Okay, very well. So today we're going to continue a new topic, which is again on kinematics, but it involves analyzing velocities in a new way, which is based on the instantaneous center of rotation. So let's say you have a rigid body, and you would somehow you got the velocities. You've used gyroscopes or whatever, and then you were able to get the velocities at different points, and then this is point A, point B, and then point C. And the velocity vectors at these points were VA was like this, VB was like that, and then VC is like this. All right, and what do you think about this? Does this sound reasonable? I mean, do you think it is actually possible to have these velocity vectors like that? Okay, so this is not possible. Why? Because the fact that you actually have a rigid body, right? Basically, the points are connected, right? And the distance between the points are not moving. Then the velocities between these points are actually going to be related together, and they are going to be related by this equation. So if I say the velocity of B, the velocity of B is going to be related to the velocity at A based on this equation, where we have VB is equal to VA plus omega cross RB with respect to A. And here, obviously, that rigid body is going to have omega. So if you actually look closely, you see that these velocities are trying to rip that rigid body apart. So it is impossible to actually have the velocities of these points. For example, could you have a car, for example, where the car is translating where the velocity of this point is like that, and then the velocity of this point is like that? Then it's impossible, right? Then your gyroscope or your velocity sensor is giving you wrong measurements. Okay, and again, these are wrong. Why? Because the velocity at B cannot be like that. The velocity of B has to be equal to VA plus omega cross RBA. So so if I were to actually plot it based on this equation, then first of all, I'm going to put VA, and omega cross RBA is going to be a vector that is looking like that. So summing these two velocity vectors, I'm going to end up maybe with something like, then this is actually VP, and then this is basically wrong, right? This is actual velocity at B. This is how it had to look like. Okay, so there are actually ways for quickly looking at these velocities and telling whether these velocity vectors are actually do actually make sense or not. And to do this, we are going to use the concept of instantaneous center of rotation. So what we can do instead is you can actually find the instantaneous center of rotation for any rigid body by simply using two velocity vectors at two different points. Let's say you have, this is point A, and you have, this is VA, and you need to know another point. You need to know the velocity vector basically at another point, and then let's say this is point B, and then point B has this velocity vector. Now that's it, right? So these two velocity vectors, they actually define the full kinematics of this rigid body. So now we can find, based on these two velocity vectors, I can actually find the velocity of this point or this point. How do I do so? The first step is I need to find the location of the instantaneous center of rotation. And to do that, the instantaneous center of rotation will always be located on the intersection of common perpendicular to the velocity vectors. So this is a velocity at A. Then this is going to be the line where the instantaneous center is somehow located. And because I have this velocity vector, now I'm going to also draw that. And now my instantaneous center of rotation is here, and I'm going to actually call it by I. And the instantaneous center of rotation doesn't actually have to occur on the rigid body. It could be somewhere outside the rigid body. And this instantaneous center of rotation, it means that at that instant, this rigid body is actually rotating about that point. and every rigid body has an instantaneous center of rotation. If the rigid body is translating, then the instantaneous center of rotation has to be at infinity. All right. How do I find the velocity of that point? To find the velocity of that point is basically now I can use my instantaneous center of rotation, and the velocities of any 2 points are rated like this. So if I choose to find the velocity at point P, I can now use VI, but I know VI is 0. So VP is going to be equal to VI plus omega cross RP with respect to the instantaneous center of rotation. So right now I'm taking advantage of the fact that I know the instantaneous center of rotation and I know the velocity of the instantaneous center of rotation is going to be 0. So the velocity at point P is going to be equal to what? It's going to be equal to omega cross RPI. So obviously, if these are perpendicular, then VP is going to be equal to omega multiplied by RPI, right, in magnitude. So the velocity of point P, all I have to do is just join this, and then this is going to be my VP. How do I find the velocity of this point? Again, using the instantaneous center of rotation, just draw a line from the instantaneous center of rotation to the point of interest, and then your velocity on that point is going to be equal to omega multiplied by that distance. And you would see that as soon as you are approaching this instantaneous center of rotation, then the velocity of your respective point would basically be 0. All right. Very well. So now I would like to give you guys a couple of questions on this, right? So we said we can always identify the center of rotation on a rigid body by knowing the velocities of 2 points, right? And, I'm going to give you guys an example. Let's say your point was here, right? And then another point is actually right below it, right? And let's say this point actually has the same velocity at this guy. Then what is the instantaneous center of rotation? Can you guys take a guess, Julien or Len?
Yes, it should be in the middle between A and B at mid distance.
No. So in the case of a rigid body which is translating, right? So when the velocity at A is actually equal to the velocity at B. What this tells you is that this rigid body actually must be translating, and in that case,
infinity.
Exactly, it would be at infinity, right? So this rigid body is rotating about infinity. Essentially, it is translating. All right. There are a couple of exceptions to this situation. Is if a rigid body is here, right? If VA is like that, and VB is like this, is in the opposite direction as VA. Okay, in that case, and this is an exception, to get the location of the instantaneous center of rotation, you actually have to continue this, and then your instantaneous center of rotation is going to be here in the middle. Okay, only in that case, basically, you have to continue this and then draw these two similar triangles, and then this is going to be your instantaneous center of rotation. And then now you can use this to find the velocity at this point, right? Which is going to be omega multiplied by IP, right? Let's say this is point P where you are trying to find its velocity. All right, and there is also one more exception. So there are two exceptions in general to this. So one way is where your velocity vectors are parallel and are opposite in direction, then your instantaneous center is here. If your velocities are parallel and equal and at the same point or along the same line, then it means that the rigid body is translating. And how about this situation where this is your rigid body and the velocity of this point is, velocity of A is like that, and the velocity of B is smaller? Then where do you think the instantaneous center of rotation? So in that case, to get the instantaneous center of rotation, you actually have to continue this and then do that, right? And then you continue these two triangles, and then your instantaneous center of rotation is here. It basically means that this rigid body is rotating about this point I. Okay, so these are the two exceptions, right? and that is it. All right. Okay, now I have a question for you guys, and if you guys answer it, I'll give you 5 points basically. Either you or Lynn, I'll give you 5 points on this exam, which is coming up on Monday. If you have a rigid body like this, and you actually have point A has this velocity, and I have point B, which is here, okay, and point B has a different velocity, and that velocity here is smaller. Okay, so VA is much greater than B, and these are horizontal, right? Okay, how would you find the instantaneous center of rotation based on this situation, right? So velocity at A and velocity at B are parallel to each other, but the velocity of point B is actually smaller than the velocity at A. How can we find the instantaneous center of rotation in this situation? So what we know right now, we know how to find them if they were parallel. We know how to find them if they were equal and opposite, and we know how to find them if they were like this, one is small, one is big. But what if that vector here is moved over here? You know, we know in rigid bodies, the velocity of this vector, I can't actually move it here, right? Because here it would be a totally different velocity. How would you get the instantaneous center of rotation based on this situation?
We can join the border of the two vectors.
We can join.
So
You
the
I know. Well, I know the instantaneous center of rotation always has to be perpendicular to the velocity, right? All these cases, مثلا هون we had the instantaneous was here. Honi we had it here, right? Honi we said it was at infinity, right? We always know that the instantaneous center of rotation has to be always perpendicular to this velocity vector, right? In all these situations, right?
Yes.
So here we know the instantaneous center of rotation. How do I locate the instantaneous center of rotation in this case? So here, basically, the instantaneous center of rotation here has to be basically along this perpendicular to VA, and here it has to be actually be perpendicular to VB. So here it's actually impossible to have an instantaneous center of rotation, right? Why? Because here I know the instantaneous center of rotation has to be located along this line, somewhere along this line, and I know that it has to be basically located along this line. And these lines are never meeting, right? In that case, I know that it is going to be impossible for these velocity vectors basically don't obey kinematics or rigid body motion. All right, so this is like you know, the fact that these two velocity vectors are parallel, it means that this rigid body is translating, right? And how could you have an object which is translating, right? Yet the velocity on this point is going to be greater than the velocity of this point. So it is actually impossible to actually have that. So this combination of velocity vectors on this point and on this point is actually impossible. For this to make sense, then this point actually has to be here. And if VB is here, then yes, you can get the instantaneous center of rotation here. But if VB is here, then it is basically, then this basically violates the kinematics of rigid body motion. And I want to actually prove it to you guys. And what I'll do is I want to say that VB, I think, Jana, you want to mute your, okay. So VB is going to be equal to VA, right, plus omega cross RB as viewed from A. You guys agree? So B and A are both in the I direction. So I can say VBI is equal to VAI plus omega K cross. Well, I know RBA is going to be this vector, right? And this vector will actually have Rx, X component, and then it's going to have Y component. So let's call this guy Rx, and this guy here, I'm going to call it Ry. So omega k cross RBA, which has x component Rxi plus Ryj, right? And if I do this, right, to see if it is actually possible to have a rigid body where the velocity of this point is actually these two velocities are parallel, but they are at two different points and they are two different velocities. So I can write this VBI, right, is equal to VAI plus omega k cross Rxi plus Ryj. Expanding this further, I'm going to end up with k cross I. So I'm going to do this cross product ijk, and k cross I is going to be equal to j plus omega Rx j, and k cross j is minus I minus omega Ryi, right? So I know the i's have to be equal, right? Or I could, like, VB is going to be equal to VA. So I know VB has to be equal to VA minus omega Ry, and I have 0 here is going to be equal to omega Rx, right? So for this equation, or for this to obey these velocities, to obey rigid body motion, then omega times Rx has to be equal to 0. So it's either Rx is 0, meaning I came back to my original assumption that for this to be accurate, then this VB has to be here, and my instantaneous center of rotation would be located here, right? Or I would have to have omega 0, right? And if omega is 0, then this rigid body would be simply what? Translating, right? So for this to be accurate, then this point actually have to be here, right? Basically, either Rx is going to be 0 or omega is 0. So if Rx is 0, then I would have to move this velocity vector and put it here. And if omega is 0, then this rigid body could not be translating, right? And I'm sorry, could not be rotating. And again, if omega is 0, then could it be possible that a rigid body is translating, right? Like, let's say you have a car, and the car is translating. Could it be possible where you have a velocity vector here is like that, and then this velocity vector is like that, and then it is translating? No, it's not possible, right? So it means that this is impossible. So it is not possible to actually have VB to be like this and then VA to be like that on a rigid body. It means that, again, this is violating the kinematics of that rigid body.
So, doctor,
Yes.
what if VB was equal to VA in magnitude? It would be translating?
If VB was equal to VA in magnitude and
Yes.
it was horizontal,
Omega
yes.
equals 0.
And exactly,
Okay.
in that case, yes, it would be correct.
Okay.
Okay, very good. So the idea here is, these are basically exceptions, and then what I just showed you right now, basically, if you have a rigid body, then the velocities on the rigid body, they would have to satisfy the kinematics of that rigid body. Let me give you an example. Let's say you have a wheel. Or a bicycle tire, right? Let's say this is a bicycle tire. We said there are two ways for finding the instantaneous center of rotation. One way is to, already the velocity vectors, and you draw their common perpendicular, and then you locate the instantaneous center of rotation. The other way is by looking at the motion of this object, and then looking at the points which are in contact with the ground, and then these points would have basically zero velocity. So where do you think the instantaneous center of rotation on this bicycle tire is located?
In the center of the circle?
Center of the circle.
Center of the circle. Why is it the center of the circle?
Because it's perpendicular to all the tangent, the velocity at the tangent.
It is perpendicular to the velocity.
To the point.
Right. Okay. What do you think the velocity of this point is going to be?
0? Or
0.
maximum?
Exactly. So the velocity of this point is 0. Why? Because this bicycle tire is always in contact with the ground, right? And therefore, this point will always have 0 velocity. Therefore, this is my instantaneous center of rotation. all right? And if the wheel is rolling to this direction, then this is going to be my omega. How can I find the velocity of this point?
We join with the center of rotation, and it will be perpendicular.
Exactly. You draw a line, and then the velocity is going to be perpendicular to this line. Let's say this is point P, then my velocity vector is going to be that, right? And basically, VP is going to be equal to how much? IP multiplied by omega, right? مظبوط?
Yes, because vi equals 0.
Because vi is equal to 0, exactly. Now, can I use this to find the velocity of the center of the bicycle wheel? O, how do you find the velocity of point O?
Also, we join with
apply the formula.
Apply the formula. So you join a line from the instantaneous center of rotation to point O, and then this is going to be your VO is going to be omega times R. ما هيك لأنه IO in this case is R. Okay. How about the velocity at the top of the wheel? Can someone tell me?
Omega cross D.
Which is what? So we again draw a line. Okay? Exactly, omega times 2R. Or 2 omega R. Okay, pretty simple. Okay, so this is what you really have to do in the case where you are dealing with instantaneous center of rotation, or you can, if you don't know the instantaneous center of rotation and then I know the velocity at these 12 points, all that I have to do is what? Just to draw common perpendicular to the velocity vectors, and the common perpendicular to the velocity vectors should give me what? It should give me
the location of I.
The location of I, and then I can use the location of I to find the velocity at any point. In fact, what you actually need in the case of a rigid body, you need to know one velocity vector. You need to know it for sure, and the other point you just need to know its direction. Okay, so let's say this is point A and then point B. If I know, like, let's say point A is 2 meters per second, and VB, I don't know VB, but all that I need to know is I need to know the direction of VB. Now I can find the velocity of B. How can you find the velocity of B based on this? Can you tell me?
Yes, we applied the formula. We have the velocity of A, and with respect to A, we can find the velocity
find VB. This is what I want. Find VB. How do you find VB here? I'm sorry, I didn't hear you. Say it one more time, Lynn.
So VB equal to VA plus omega cross RAB, BA.
Okay, but you don't know omega here. You don't know omega. I didn't give you omega. How can you find the velocity of B here?
We should locate the center of rotation.
Bravo. We should locate the center of, yes, exactly. Excellent. So it's going to be here, Maheke. Why is it going to be here? Perpendicular, مظبوط, it is the intersection of the perpendicular to the velocity vectors. So you draw, this is a perpendicular to this velocity vector, Maheke, and then this guy is here perpendicular to this velocity vector. And I know the instantaneous center of rotation is here. Now, how do I get omega?
We apply the formula on point A.
Bravo, exactly. What I know, VI has 0 velocity, then I know VA is going to be equal to omega times what? IA, right? So omega is going to be equal to VA over IA. Well, I need to give you IA, right? So if I don't give it to you, just measure it, right? So we need to know IA, the dimension between them. And then once I know IA, how do I find the velocity at B?
We reapply the formula on point B.
Exactly.
Then now knowing omega.
Exactly, omega multiplied by IB. Obviously, you need to know IA and IB here. Is that all clear?
Yes.
Okay.
Yes.
All right. Excellent. Let us do a problem, okay, or look at what we have in the book. So now I'm going to start sharing my PDF. Okay, so this is a topic that we have, instantaneous center of 0 velocity. So this is a picture taken of a bicycle or a bicycle tire. I want to ask you guys a question. Do you think when the guy who took this photograph, do you think was he moving with the frame that is connected to the bicycle, or was he stationary? And why? Right? So
He's moving.
is he moving with the bicycle when he took that picture? Okay, so I'll tell you one thing, okay? So if you are taking a picture, right, of this bicycle, if you were actually moving with the bicycle, right, then the camera is going to have the velocity of the bicycle. So anything that is actually moving with the velocity of the bicycle then will appear not blurry, right? And the ground will appear blurry, right? It's like you take a picture from the car on something very close and it's going to appear blurry to you a little. So here, if you are moving with obviously the bicycle here is made of several rigid bodies. One of them is the wheel and then the frame itself and then the person of the car. If you are actually moving with the bicycle, then what will appear not blurry is the frame of the bicycle and then the center of the wheel, right? But if you were stationary, if the photographer is stationary, then the points on the bicycle which are not moving are going to appear crisp, like basically not blurry. And this is indeed what is happening, right? You see that these sprockets on a car, on a tire, they appear to you more in focus, right? Or they are not just in focus, but they appear to you not blurry, right? Versus the top here is more blurry. Why? Because you are on the ground frame, right? The photographer is stationary, and the points which are stationary on the bicycle, they are going to look better than the points which are moving on the bicycle. Does it make sense? Okay. So here.
So you meant that. So you meant the photographer, if he was stationary when he took the photo, or he was moving with respect with the bicycle?
So the question was that, right? But we said if the photographer was moving with the bicycle when he took that picture, right, then the frame of the bicycle would appear not blurry, right, because he's moving with the bicycle. Was good?
Okay. Yes.
Okay. But so what we see here in that picture is that the bottom of the wheel is not blurry, right? And we know the bottom of the wheel is going to have zero velocity. So therefore, the photographer is sitting on a frame that has zero velocity, meaning the photographer is on the ground, right? So the velocity on the ground, and his camera is capturing well the velocity at the bottom of the wheel, which has zero velocity. Okay, so here what we know again is we know we can locate the instantaneous interpretation by, like, if these velocities were provided to you, all you do is just perpendicular to the velocity, and you just need two velocity vectors. Okay, once you have two velocity vectors, the rest of the velocity vectors, they actually have to obey this, right? You can't have any velocity here, right? You have these two velocity vectors. This is a rigid body, therefore the velocity at this point has to be basically and by the way, I think the time is gonna end up a lot soon. And once that end up, basically just come back and then log back in over here. Okay. So this is what we have been trying to discuss in this lecture. And again, this is instantaneous interpretation. We've done that. How about here, right? Can you guys guess why the instantaneous interpretation is here? It's pretty simple, right? So this is a bar, right? And the bar is sliding down. And what is happening is that the velocity of B has to be downward, right? And then the velocity of A has to be in this direction. Then therefore the velocity, or the instantaneous interpretation, is going to be located that way. How can you find the velocity at the center of the bar based on what is happening right now? How can you get the velocity vector at the center of the bar?
We join the center with the center of rotation, and we do the perpendicular.
Exactly. Just identify this point. Let's call it like point P, right? And let's say point P is here, right? And what you have to do is you're gonna join this IC with this point. You get its length, right? And your velocity vector has to be perpendicular to this, right? And then this is your velocity at point B. Okay, how do you get omega, for example? You get omega here by
Applying the formula on point A or B.
exactly by applying the formula on point A or point B. Let me just make sure that this is actually recording the session. Okay. Okay, very good. Excellent. Okay, very good. So I think now we can jump in and then we can, so, you know, this is what I was explaining to you guys earlier, right? You can always find the instantaneous rotation by the intersection of the common perpendicular to the velocity vectors. We have two exceptions. The two exceptions occur where the velocity vectors are parallel, right? And one is in opposite direction. In that case, your IC, you just complete those, and then these two would be like, you know, similar triangles. And the other case is where the two velocity vectors are also parallel, but one of them is smaller than the other. In that case, your IC is going to be located that way. The other one is where here velocity at A is equal to the velocity of B. It means that your instantaneous center of rotation is going to be located at infinity. Essentially, an object is translating. It means that it is essentially rotating about infinity. You could, I guess, think about it that way, right? Okay, let us guys work on this problem right now and then see how we can solve this one. So here we have this plate, and this plate is these are sliders basically, A and B, and or slots. And we're trying to find the velocity of point D based on the velocity of point A. So how would you guys think about this problem? So we're trying to find the velocity of D. Can you guys tell me how can I solve this?
We find, first of all, IC by drawing the perpendicular, knowing VB is downward.
Bravo, yes. So knowing that VB is downward, right? And I don't know its value, Maheke. I just know that it's going down.
Yes.
How can
Yes,
I
we know
find
the direction.
How can I find the instantaneous center of rotation right now?
Joining the perpendiculars of the two.
Exactly. So VA is like that. So I know this guy is going to be along. Let me actually change these colors. I'm going to make them blue. And this guy is going to be, maybe not blue, let's make it black. Okay. So this point is going to be, this is a common perpendicular, right? And I don't know where it ends, right? So this obviously is going to be a long line, and then this guy is going to be here, right? Then my instantaneous center is going to be here. And let's call it I. Okay, so very good. So we need to find the velocity of the point D. How can I find the velocity of point D right now?
We apply the formula on point A to find omega.
Okay, how can you find omega? So, okay, let's do something. So we're going to say that VA, my K, is equal to omega multiplied by IA, right?
Yes.
Okay. So omega is going to be equal to VA divided by IA, right? Okay, what is VA?
It's given 8 meters per
meters.
second. So
Okay,
8
so
I.
we need to know IA. What is IA? We need to know this distance, right, from here to here. Right? How do you know this distance? Oh shit. Sorry about that. So this just went. Okay. We need to know this distance, right? IA. How do I know this distance IA? What is this angle?
$30.
30, exactly.
30.
Right, so this angle is 30. And how do I know the distance IA? So I think it's going to be 0.3, right? So let me rewrite that. So basically what we have here is that we know VA is going to be equal to omega times IA, right? And omega is going to be equal to VA divided by IA. And we need to know IA. IA is going to be equal to how much? 0.3 multiplied by cosine 30. You agree? Right? So omega is going to be equal to 8 divided by IA, right? by 0.3 times cosine 30. Okay, so we got our omega. Now we need to get the velocity at d. How do I get the velocity at d? I need to know id right now, right? مظبوط. We need to know the distance between id.
Can't we do it in two ways? We have the velocity of A also, and we have the omega.
Yes, but you still need to know the distance between D and A, right? Here, this simplifies things a little bit. Why? Because now we can say VD is going to be equal to how much? Omega multiplied by what?
ID.
ID, bravo, مظبوط. Omega multiplied by that. So now I need to know the length of ID. How do I know the length of ID? I need to basically look at the geometry of this, right? And one way we can do is basically we can have a frame here at the bottom, right? This is, I'm gonna call this point O, and basically let me just throw this. So this is could be my X and then Y frame, and okay, so basically what I can do is I can get actually XI, and then I can get XD, YI, and then YD, and then I can use Pythagorean, right? And then say the length of ID is going to be square root of XD minus XI squared plus YD minus YI squared, based on the frame that I drew. So I think XI is going to be equal to how much? XI is going to be equal to 0.3.
0.3 sine.
مظبوط, exactly. How about YI? 0.3 times cosine 30, right?
Sine 30, yeah.
How about XD? XD is going to be equal to, if you look at this segment on top, it's going to be 0.3, and then this angle here is 30, right? It's going to be 0.3 times cosine 30.
Cosine.
Right? How about YD? So YD is going to be equal to YI, مظبوط. YI, which is given to me as 0.3 times cosine 30, plus how much? Plus 0.3 times sine 30. You guys agree?
Yes.
Right, so this distance, right, plus that distance, right? This guy here is YI, right, or 0.3 cosine 30 plus 0.3 sine 30, which is this guy from here to here. Okay, I'm going to draw it better. Okay, guys, so now if you were to get the velocity at D, then the velocity at D is going to be equal to omega multiplied by ID, right? Or omega multiplied by square root of YD minus YI square plus XD minus XI square. Okay, guys, so that is it for this lecture, and I think